if you're looking through a band of refraction, the lower you go, the worse that refraction is, because it's hotter at the surface, whether it's water, land, or pavement. Let's take a look. So he's standing up, and you can see pretty much to the end of the street, and you can see it kind of curve around here, even though you do see some refraction happening already. Once he lowers the camera, you'll notice the refraction band increases and the visibility decreases, and you can no longer see at the end of the road, and you have all sorts of distortion. Let me get it paused here. Distortion, curvature, almost distortion, hook. I almost call this a fish hook effect, and you can no longer see the backside of the road. It looks like it goes on forever, but that's just distortion. And the only difference is he lowered the camera down, which increased the distortion refraction, because, like I say, refraction is stronger, if you will, at the lower you go. The higher you go, the less refraction you're looking through. 2, the farther out you go, the horizon rises due to perspective. So let's take a look at some images and see what we mean by that. What the horizon rises due to perspective. Okay, so what we can use, the way we can use these inferior mirages is in many observations and images and videos, we can get different height in inferior mirages, and I'll explain what that means and why. So if you notice in this image, we have a guy on a ski jet, and if you notice, the inferior mirage is here, and then as you go a little bit further out, there's a boat or some sort of object in the distance, and the mirage actually increases in height. And it doesn't really make sense, you know. Otherwise, you know, if you're talking about a ball that's supposed to be bending away the moment you go, it goes away from you. But this is due to perspective. It's due to the fact that the horizon, this water is flat all the way up to a certain point until the horizon would stop due to being flat, and then it will basically level out. But we see the increase in height, and then even way back here, this is many miles. This could be 8, 9, 10 miles or so in the distance. We see the inferior mirage cutting these things in half, and basically duplicating the top half on the bottom, and you can see very clearly over here this object has duplicated itself. So again, different height depending on the distance. So the closer you are, the lower the closer you are, the lower the inferior mirage, and the further you go out, the higher the mirage appears due to perspective. Let's take a look at one more to get the point across. So here we have a few miles. We have this bird in the water, and it's got cut in half here, and it's very close to you know, the observer, at least a lot closer than the other observations. Here, about 6 miles out, we have some inferior miraging going on with these trees. 10 miles, we have this building here with these windows, and 12, the last building, cut in half, and it matches perfectly with perspective. I mean, 12 miles out, you should not have an inferior mirage line this high up. It should be dropping instantly away if it's on a ball. And then the black lines just represent the lowering of the buildings due to perspective, and the rising of the base due to perspective as well. Let's take a look at this video, right? Another Phuket Word. He lines up these bottles, and as you can see, they're all the same bottle, same brand, and the same height, and they appear to drop due to perspective. So that one, again, is pretty simple. All right, 4. As objects get farther out, the diffraction limit sets in, and the object merges into itself. So what does that mean exactly, and what is the diffraction limit? So diffraction limited system, the resolution of an optical imaging system, a microscope, telescope, or camera can be limited by factors such as imperfection in the lenses or misalignment. However, there's also a principal limit to the resolution of any optical system due to the physics of diffraction. An optical system with resolution performance at the instrument's theoretical limit is said to be diffraction limited. So let's look at another sort of explanation and example. So basically, this means that the farther away something is, the less light is emitted into the lens, and it's harder for the lens and the aperture of the lens specifically to receive that light. And what happens is, as things that are close are, call it individualized, as those things get further away and smaller, and you have light diffraction, those objects which have not physically moved start to merge together, like this. And this is something that we've seen many times before, and again, talking about boats going over a curve. Let me see here. Wrong. When we're looking at something like this, and right here you see the detail of the boat, you see the whole of the boat, you see the top, you see lights, and as that boat gets further away, I mean, already it's only, say, a mile away or whatever, and the detail is just not quite the same. And then when it gets much further away, there's basically no detail. This is the diffraction limit of the camera, the light that's being emitted, going through the atmosphere, etc. It just can't resolve it. And lastly, 5. The object above an inferior mirage is sitting on top of the water and is not dropping. So let's take again a look at a couple of pictures. So this picture is showing a car coming at the cameraman or person from a sort of an unknown far distance, maybe 3 miles, 4 miles, and then coming in each subsequent shot closer, closer, closer. So we can really deduce a lot from this image. Let's start down here where the car is actually a little bit closer than in the last image. So what we can see here is that the black line that I've drawn in each of these squares is the inferior mirage line. It's the line that separates the real object above from the refracted, mirrored object below. And we know for a fact that the object above is the real object. It's not loomed or super loomed or a hologram or anything like that. You cannot have a refracted image refract upon itself. That's just not possible, the way that the refraction and light work. So let's take a look at some of the things that I've already outlined and see if we can pinpoint some of the points. So as the car, if we go in reverse as the car is getting farther away, we can see it's already converging into itself, right? The closer you are, the horizon and the refraction, the mirror image is bigger, and the further out you go, the closer the refracted image, the inferior mirage, gets to the actual real image that's still above the line, right? And that's due to the diffraction limit, and possibly I didn't mention Rayleigh criterion. I sort of get those two mixed up sometimes. So whether it's the diffraction limit or Rayleigh criteria or both, basically as the object goes further out, it blends into itself, and you can no longer make out. I mean, at this point, you don't know if this is a car or a spaceship, right? Here you know it's a car. Here you know it's a car. Here okay, it still looks like a car. Here, the headlights have merged into one. And we know it's not one giant, those are big giant headlights. We know it's the merging of the inferior mirage with the real object. And as it goes further, it blends in more and more. But notice it's never dropping. The horizon line is pretty much in the same spot the whole way. And it's, it's at this point, it's just a blob. You don't know what it is, but it's not disappearing over a curve. It's just if this kept going back, this would eventually disappear into a little point, and you wouldn't see it anymore due to perspective, the how far it is, and the atmosphere, and blocking it, and light not being able to get to the lens of the camera. So now that we have sort of looked at some of those points and can see this, and now on a flat surface that we know is flat, let's take a look at some snippets of a video I took of a boat going over the supposed curve. And let's see how many of those same phenomena we can spot. So in this image, again, like the car in the bottom right, and the top now is in the top left of the boat. This is the real object. And here we see the black line separating the real object from the inferior mirage. And also notice that the water line doesn't rise all the way up to where the horizon is. This black line is the horizon. The boat isn't floating in midair, right? Due to refraction, it's blending the sky into the actual body of water. Now, take a look at this as we go further, as the boat's going further out into the ocean. Notice how the horizon line is actually increased in height right? That doesn't make sense if it's a ball. It would be going down. In fact, this whole object would have already gone, I don't know, halfway around the ball, but you still see the entirety of the boat. Now, it is still cut in half, but again, this is the real object, and you can't see anything that is, call it quote unquote hidden, is either hidden behind this refraction zone or line, this mirroring effect, or it's simply going into that Rayleigh criteria, that diffraction limit, where you can no longer see the object clearly. It's just gone too far into the haze. And again, notice the distance of what looks like the horizon water line from there to here. This is the real horizon line. The boat is not floating in midair. Okay, now we have it here. Now look at this. Okay, so this is where people would come and say, oh look, we've looked out, the boat's 4 or 5 miles away, you know, it looks like a smudge, and this is the top. They would say this whole thing, this whole square is the boat, and it's kind of going over the curve, right? It's getting smaller. No, again, the black line is cutting the boat in half. This square is the full size of the boat still, and this is the inferior mirage. And again, the gap between the water line and the inferior mirage line has either increased again a little bit, or at some point it will even out and it will not increase anymore, because this is the level plane that it's on. So this water from the cameraman to this point is completely level. Now mind you, this is many miles out at this point. Even in the top left, it was, I don't know, 3 miles, and it's only going further and further. And we know how the ball math is supposed to work, is at an exponential rate. Now here we have this one. Now this is an image that, again, most people would look at on the globe side and say, well, look, the boat's going over the curve. We can't see it anymore. All we see, or they would say something like, all we can see is the top of it. You know, here's what you should see, and we can only see a little speck, right? It's just the top, it's gone over. Well, again, but it hasn't, right? This is an inferior mirage line. The bottom half is mirage, the top half is the actual object. The actual object is sitting on the flat plane of water. It's not gone over any curve, just like the car in the previous image. And here's the supposed, you know, this is what, again, people would say, look, here's the horizon, it's where the water stops. Well, no, we know that's not true. We know it's a mirage. From here, the water line up is a mirage, because the boat isn't floating in midair. And the reason we know that this is the whole object is because, again, you cannot have an inferior mirage of a mirage. This is only and can only be the actual boat. Okay, so let's take a look at that video. Let me see. I actually need to grab the clip.
In the curve.
That's the wrong one. All right, so let's watch the video together, and we'll kind of go sort of a play-by-play. Now already this boat's a few miles out. He's got a pretty massive zoom. It's probably like a P900 or something, and he'll zoom out in a minute. We can see how far it is. It's already, I would say, at least 3 miles, maybe further, 4 miles already. So again, we can see already the inferior mirage line starting. And as we discussed earlier, the further out the boat goes, the higher the mirage line will increase. The boat will appear to get smaller due to perspective, and everything just sort of makes sense when you're talking about a flat body of water or a flat plane. Perspective lines increasing, and the boat decreasing in size due to perspective and disappearing due to diffraction limit, Rayleigh criteria, and those kind of things due to the atmosphere. So let's keep playing it. And I'll skip ahead a little bit here. I'll put the link. Oh, here he is zooming out, so I'll just let it play through. And you can see the inferior mirage line. So he's zoomed out. I mean, look how far that is already. That's at least 3 miles. I'm gonna fast forward it a little bit. Okay, so now we can see the clear mirage line splitting the boat in, call it in half, or at this point, about the midpoint here. Keep playing. Fast forward a little bit. So now it's going to go behind this boat. Now watch this. Look at this. It's already, I mean, the bottom of the boat, right? You can't see it. It looks like this is the entirety of the boat, but it's not. The boat is at this point and above where my cursor is. That's the real boat. Anything below that is the inferior mirage, and we've demonstrated that using images and science and reasoning. And so someone would look at this and say, oh look, the whole boat, you can't see the bottom of it, it's because it's over the curve. No, it's not over the curve. It's the boat's rising. It appears to be rising due to the due to perspective. It's on a flat surface. So let's go play. It's gonna go behind this boat and kind of get stuck back here a little bit, and then it'll pop out again here in a second. And I'll pause it. And when I pause it again, that's when it really has kind of diminished in size, and you really can't even tell what the heck it is anymore. You don't know if it's a 10-foot boat or a 50-foot boat. You would never be able to tell. Here, where are we? It takes a while to get past it. I mean, you just imagine the speedboat is just going, what, 15, 20 miles an hour. Well, look at that. I mean, what is that, right? It's a blob. And is it a floating blob, right? I mean, this clip makes no sense, right? If you're thinking about a ball, it just makes no sense. We know that the inferior mirage is about right here at this, call it the midpoint, maybe slightly below. And everything from my cursor again down to the water line is all refraction. The water doesn't stop here. The water stops here. You just can't see it because refraction has blended the color of the sky in with the sort of call it top portion of the water. And the boat's gotten smaller due to perspective, and it's starting to haze and phase out due to the atmosphere, due to the light not hitting being able to hit the camera anymore. And then it goes on. He zooms back out. Play. Look at this. It's just gonna disappear. It's in the atmosphere. But look, it's not dropping over anything. It's still sitting here, floating, if you will. It should be going down, and it's not. Let it play. I mean, now we've got like this weird TIE fighter looking thing, right? I mean, what is going on here? Clearly, the boat, you cut the boat in half and you still have the whole boat, call it visible to some degree, minus the fact that you can't tell what the heck it is because it's all converged together, just like in the image of the car that we saw. It's all been combined, and then eventually it just disappears. And not because it's gone anywhere, not gone down anywhere. It's disappearing because the camera can't see that far, so to speak. The light from the boat is not getting to the camera any longer because of the atmosphere. And it's really that simple. And now it's gone. And people would say, oh, that boat went over the curve. No, it never dropped once. It only, in fact, appeared to rise due to perspective.
What is an inferior mirage, and how does it prove the cliffs were not behind the curve? The hot tarmac road, inferior mirage, is the situation most people have witnessed. On a hot sunny day, that tarmac or concrete road absorbs the sunlight, considerably raising its temperature. The hot road heats the layer of air directly over it. This results in an air density gradient that consists of a layer of hotter, less dense air above the road, underneath a layer of cooler, more dense air above it. The light reflecting off the car and passing through the density gradient is refracted in an upward direction, resulting in an inferior mirage, being observed as illustrated below. Sunlight reflects off the car. Light refracts in an upward direction. Human brain assumes light travels in a straight line and sees the refracted image at the end of the green dashed line, called an inferior mirage. An air density gradient is present. Cooler, more dense air is above warmer, less dense air. The light changes direction in an upward direction relative to its prior direction of travel. This type of refraction produces an inferior mirage. The refracted image is always observed inverted and below the actual object. Simple way to remember: image below object equals upward refraction of light. This is a proved and known scientific principle. The inferior mirage over water. Another example of the upward refraction of light. A portion of light from the sun is reflecting off of the buildings and land and traveling out to sea towards the observer. Light rays initially traveling downwards towards the sea will pass through the density gradient and be refracted in an upward direction. This results in the viewer out on the sea looking back at the land observes an inverted image known as an inferior mirage. The refraction of light in an upward direction. Note, below the yellow line is actually sea, but it cannot be observed because we are observing the inferior mirage of the boat in front of it. The same as on a hot day, it looks like a pool of water is in front of a person standing on the black tarmac. Were inferior mirages occurring along the coast? Inferior mirages can be observed all along points of the coast in the video footage. Inverted images can be observed underneath the actual objects, the cliffs, which occur due to the refraction of light in an upward direction. The red line is termed the mirror line. The actual object is above the mirror line, and the inferior mirage inverted image is observed below it. Summary. An inferior mirage is always observed inverted and below the actual object. An inferior mirage is observed because light reflected from the object refracts in an upward direction as it passes through a density gradient. And what does this prove? If the object was behind the curve, it would not be possible to observe the inverted image, the inferior mirage. Proof of an inferior mirage and light refracting in an upward direction is an observed inverted image under the actual object, which is easily detected by drawing an appropriate mirror line through the picture. The green line represents a ray of reflected light traveling in a straight line. The pink line represents the path of a ray of light being refracted in an upward direction, which is necessary if an inferior mirage is to be observed. If the actual object is behind the curve, can the ray of light refracting in an upward direction be observed by the camera at point B? No, it will obviously travel over the camera. If the light refracting in an upward direction travels over the camera, will an inferior mirage be observed by the camera? No, obviously not. On a globe, it is not possible for an inferior mirage, an inverted image underneath the actual object, to be observed because the ray of light refracting in an upward direction will not enter the observer's eye or device. However, it is possible for an inferior mirage to be observed as an inverted image underneath the actual object at a distance of 44.2 kilometers or 27.4 miles over a flat surface. Would light being assumed to bend around the curve produce an inferior mirage? No, it will not. If this was occurring, then only a normal image will be observed as illustrated in the diagram below. Is it at all possible for an inferior mirage to be seen on a globe? Note, for an inferior mirage to be seen, the ray of light must be refracting in an upward direction as it enters the observer's eye or device. For the light to reach point B from point A, the following stages would have to occur. 1. The sunlight reflects off the cliffs and travels around the globe. 2. The light then starts to refract in a downward direction due to the sudden presence of a vertical density gradient. This does not ever happen under normal everyday conditions in the UK. The light then starts to refract in an upward direction due to an immediate inversion in the vertical density gradient. This does not ever happen under normal everyday conditions in the UK. 4. But this would only result in inferior mirage, inverted refracted image, being seen by the observer and not the actual object, and this does not happen. Are there any photos that show this? No. Applying the known scientific principles of light, refraction, and density gradients at sea, it is not possible for an inferior mirage, a downward inverted image, to be observed underneath the actual object under normal, non-specialized, non-manipulated atmospheric conditions on a globe. If anyone says it is possible for an inferior mirage, downward inverted image, to be observed underneath the actual object on a globe under normal, non-specialized, non-manipulated atmospheric conditions, draw a diagram for them as illustrated below and ask them to sketch on it how it will work, following the known scientific principles. 1. The observer must see the actual object and a downward inverted image, inferior mirage, underneath it. 2. The rays of light that result in the observer seeing the inferior mirage must be refracting in an upward direction as they enter the eye or device. And 3. The density gradient must be vertically identical across the surface of the water from points A to B. When a person cannot do this, they will engage in one or more of the following: obfuscation, deflection, word salad, direct you to a model. If they attempt any of the 4 points above, ask them for their own personally empirical evidence to support what they are saying. When you don't receive it, which you won't, you will immediately know the person is disingenuous and lying. No known scientific principles can be applied to this observation that disproves that we do not live on a globe, or similar-sized oblate spheroid ellipsoid, with a radius of approximately 6,371 kilometers, or 3,959 miles. It is incontrovertible, unless you are a science denier.